Okay, in this video, we are going to look at the mathematical definition of a Moore machine. Remember, we have already looked at the mathematical definitions of DFA, NFA, and epsilon NFA. And now we are going to look at the mathematical definition of a Moore machine. Okay, so remember, every machine in TOC will have a mathematical definition. So later we will also look at the mathematical definition of a Mealy machine. Okay, so you have to be very careful that you know all the mathematical definitions and how each one of them is different from the other. So it's going to be very important. Okay, now let us learn about the mathematical definition of a Moore machine. So while learning the mathematical definition of a Moore machine, we will be considering this Moore machine, which we already seen in our previous video, which will count the number of A's. So as you can see here, this is the Moore machine, which will count the number of A's in a given string. Okay, so once we have completed our mathematical definition, we will understand its implications using this Moore machine. Okay, so the mathematical definition of a Moore machine is somewhat similar to that of a DFA. Okay, so let's look into it. So again, sigma here, sigma here is the set of alphabets that you're using. So in this case, it is going to be A and B. Okay, I'm connecting the mathematical definition with this particular Moore machine. Okay, and remember, Q is going to be the set of states in your machine. So in this case, we have only Q0 and Q1, Q0 and Q1. And here comes the transition function, which is delta. Okay, so we know that delta is the transition function. We have defined transition functions for DFAs, NFAs, and epsilon NFA. Now, remember, very importantly, the transition function delta here is same as the transition function of a DFA. That means delta is defined from. Okay, so let me make it very clear. Delta is defined in the same way as that of a DFA. So delta is defined from the Cartesian product of Q and sigma to Q itself. This is very important. So remember, this is the delta definition of a DFA itself. Okay, so this means that transition function should be available for every state. Okay, so transition function must be available for every state. That should be guaranteed, right? So that's a property of a DFA. So this is going to be the same transition function as that of a DFA. So this is very important. Again, what about the final states? Is there any concept of a final state in a Moore machine? No, we don't require any final states at all. So we don't have such an entry in our mathematical definition. We have to also indicate the output states. Look at here. In our Moore machine, we have an output at Q0, and we have outputs at every states. For Q0, in this case, we have 0 as the output, and for Q1 we have 1 as the output. So we should have a representation for the output states. Okay, so what we are going to do is we are going to represent the set of output states using the letter delta. Okay, so it is indicated like this. So capital delta is going to represent the outputs, and in this case we know that it is 0 and 1, right? Because the outputs are 0 and 1. So in this case, it's going to be 0 and 1. And remember, there is one more function. Okay, so we call it as a lambda function. Okay, so the lambda function is called the output function. Okay, so it's called the output function. So it is needed to actually specify the output. Okay, so given a state, we can given a state, it is associated with an output. So the definition of an output function is very straightforward. So given a state, it is mapped to one of the outputs. Okay, so for example, if you are given with, suppose if you are given with Q0, okay, Q0 is actually mapped to 0. Okay, so So in general, we can say that capital Q is associated with delta. So it means that given a state, it is always associated with an output in your output set. Okay, so in this particular case, Q0 is always associated to 0 and Q1 is associated to 1. Now it is possible for us to write the mathematical definition by summarizing all these facts. So it is going to be, I can write it as M equal to, okay, so it's going to be very similar to that of a DFA. So we'll have a sigma Q Q0 delta which is a transition function, and we don't have final states, right? We will not be having a final states. So instead, we will be having the output set as well as the output function. So the other than the transition function, you also have an output function which is going to be lambda, and there is an output set which is represented by the capital delta. Okay, so this is how we are going to represent the mathematical definition of a Moore machine. Remember, this has got 6 tuples in it. So this is actually a 6 tuple definition. This contains 6 tuples or 6 variables, right? So it is going to be a 6 tuple definition. Remember, very importantly, that lambda is the output function. Lambda is the output function which is defined from Q to delta. And delta is the output set which is a set of all the probable outputs, right? So this is going to be the output set. So these are the only 2 variations from the DFA definition. And again remember that we don't have a final state here. We don't have final state in this definition. Instead, we have got an output function and an output set. So this is going to be very important. So this is how the mathematical definition of a Moore machine is done. So again, it is very important to remember that delta here is very similar to the DFA. So I'm writing this the second time because to emphasize it. So delta is actually defined from Q cross epsilon, Q cross sigma to Q itself. So this is going to be very similar to the DFA definition. The transition function is defined exactly as in the case of the DFA. As in the case of the DFA definition, right? So this means that from every state, you should have transitions for all the symbols. Okay, so in this case we have got A and B in our alphabet set. So we should have the provision of having transitions on A and B from all the states. And very importantly, you cannot have epsilon transitions because delta function is defined only from Q cross epsilon to Q. There is no concept of an epsilon transition. So we don't have epsilon transitions. We also don't have multiple transitions. We don't have multiple transitions. So the properties of epsilon NFA and NFA, that's what I'm going to emphasize. So don't think that your Moore machine will have multiple transitions. It will not have multiple transitions. It will not have epsilon transitions. Also, you cannot leave out a transition, right? So all these were properties of NFAs and epsilon NFAs. Okay, epsilon NFAs. So these properties are not there for a Moore machine and a Mealy machine. So the transition function of a Moore machine is defined like this. This is exactly the same definition in the case of a DFA. So this is going to be very, very important.